All right, so we are going to get started. Just a couple of announcements. We will not have an assessment next week for finals. I know that breaks your hearts. Please try to fight through that depression. Okay, um, I know it's just a letdown, but no final. Um, and then the third trimester will be back to hybrid learning. So, cohort A, odd hours, cohort A, even hours. Um, then that flex day on Wednesday, I think will stay the same from my understanding. Um, and then cohort B, Thursdays and Fridays. So those of you who are signed up for hybrid, that um, kind of similar to what we did in the fall, that schedule will be what is followed. If you have questions, feel free to ask. If you want to wait until after class, you can certainly do that as well. Um, any questions on homework? All right, we're going to start today with the fundamental theorem of calculus. We started studying calculus back in September. Here we are in March, finally getting to the fundamental theorem of calculus. And today's assignment, hopefully, you'll find to be pretty straightforward and relatively easy. Just some information. So Isaac Barrow, who was Newton's teacher at Cambridge, kind of discovered the link between derivatives and integrals. And he was the one that realized that derivatives and integrals are actually inverse operations. And not anything that you need to remember here or have memorized. It won't be on a test or a quiz, but just the idea that just some background information as we move forward. So some properties of integrals that can be very useful as we um, move forward. Um, if you have the integral from b to a of some function f of x dx, that is the same as if you take the opposite of the integral from a to b. So you can change the limits around and just put a negative in front. And if you think about this should make sense, because on the left-hand side, that would be, our capital F of A minus capital F of B. On the right-hand side, it would be the opposite of the quantity, capital F of B minus capital F of A. So that negative would work out. The integral from a number to itself is 0. So if you have the integral from 2 to 2, it doesn't matter what your function is, it's 0. We've talked about a couple of these, I think, already. If f is greater than or equal to 0, for any x on an interval from a to b, then the integral of that function is going to be greater than or equal to 0. If we have a function f that is always greater than another function g, again, for all x on an interval from a to b, then the integral from a to b of f is always going to be greater than or equal to the integral from a to b of g of x. The last one here, if our function always, if it has a minimum and a maximum value, so it's always between this value little m and this value big M, then the integral will always be between little m times the length of the interval and big M times the length of the interval. So the value of the integral, again, if you think about it in terms of area, which is, just one of the ways to think about integrals, what it's saying is the area under f of x is between the area of the rectangle formed by the minimum value of that function and the area of the rectangle formed by the maximum value of that function. We've got this is little m, this is big M, so your area under F has to be between this, that lower area and this upper area. All right. So the fundamental theorem of calculus, which actually comes in two parts. The first part says if we have a continuous function f on the interval from a to b, then the function g that is defined as g of x is the integral from some value a to x of f of t dt, where again x is somewhere on that interval from a to b. So g is the antiderivative of f. That means that if I take the derivative of g, I get f for any values from a to b. Probably doesn't sound earth-shattering, but it's actually pretty helpful. So you might get a problem like this. Find the derivative of g of x given g of x is the integral from 0 to x of 1 plus t squared whole thing to the 1/2 power. And to do that, to find g prime, A couple of things. The x has to be the upper limit in our integral, which it is, so that helps. We're going to take everywhere in our integrand that we see a t, we're going to replace it with x. And that's it. That's our answer. So again, that part one of the fundamental theorem of calculus. If g of x is defined as the integral of f of t dt, then g prime of x is equal to f of x. The second part is the evaluation theorem that we've talked about. We talked about in 5.3. If we have an integral from a to b of f of x dx, that is the same as capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is, capital F prime is equal to little f. All right, so some things that can happen with the fundamental theorem of calculus. So here we have g of x is equal to the integral from 3x to 0 of sine of t dt. Find g prime. So, excuse me. The first thing the fundamental theorem of calculus tells us, we need that x to be our upper limit. So we need to get this moved to the upper limit. And we can do that with one of our properties that we just looked at. We can change the limits by putting a negative out in front. Then the derivative of g is going to be our integrand with 3x put in everywhere that we see a t. However, because we have a function in our upper limit, we also need to multiply by the derivative of that function. So in this case, we do have to take the derivative of 3x, which is 3. So if you want to jot down, if we have g of x is the integral from 0 to some function of x, let's not use f there. F of t dt, then g prime is f of h of x times h prime. It's a chain rule idea.